So we may begin.
Hello, our project is video colorization, and our team is Daniil Tyapkin, Anton Zbekhin, Ilya Levin, Timofey Grinev. Color stylization plays a critical role in modern cinematography and video storytelling. It has a powerful ability to grab audience attention, elicit emotions, and convey implicit mood. One of the main use cases of video colorization is to give a second lifetime for our beloved films and family videos by turning them to color from black and white. It is not hard to simply colorize such videos. The main catch is making colorization believable, consistent, and true to the reference, almost all of which are known to everybody by default. Our main goals are to implement and somehow enhance modern techniques of black-white video colorization using the mix of spatial and temporal convolutions and GANs with problem-specific losses and experiment designs. First of all, there are a lot of colorization approaches known right now. All of them pretty much use a reference image that somehow is connected to the output images from black and white. Some of them propagate only through the first frame. Some of them are attention-based and are referred to every issue frame. Some of them use temporal source reference attention, and there are a lot of references. However, it is important in video colorization to make it consistent throughout many frames. So there is a big amount of spatial temporal correspondence methods, such that use special losses or architectures to preserve consistency in time. For example, this work named temporally consistent video colorization. It uses a span of some number of input features, for example, 4, and it propagates in both directions in order to features to be connected to each other, and there would be no flickering or image or color distortion.
So for the training and testing of our models, we take a Davis 2017 dataset, which consists of 90 videos, which are initially proposed to be used in segmentation and object detection tasks, but in many papers which address the video colorization issues, this dataset is also used. For the final test, we decided to take the black and white film by Andrei Tarkovsky, Andrei Rublev. So to begin with, we took the well-known Colorization network, which is designed to colorize individual frames, like individual images. Even so, when we have just a single image, there is no such thing as temporal or spatial consistency. Still, the problem of colorization of black and white images is ill-posed, as there are many possible ways to transform each pixel into the color space. So the existing model CIC, the colorful image colorization, tries to address this issue by using convolutional neural network and regression in the space of color features as a mapper from the neural features to the color space. So we decided to stick to this architecture as a backbone for the most part of the methods that we tried to check. So as it was mentioned before, one of the architectures, it proposes to use a FlowNet network, which predicts the optical flow between consecutive images, and then we can warp the coloring features of a number of images with an optical flow to somehow reweight them and refine these features all together. So the feature, the color feature for the given frame takes into account the frames which come before and after it. In addition to that, for the regularization purposes, to make the flickering disappear, we can also use a discriminator on top of this colorization network. So the two networks might be trained in adversarial fashion to address the flickering issue and make colorization of each frame more realistic. But we may still try to use something more easy. For example, we may just inpaint every single frame as it is, but then when the colorization is performed, we can warp each frame into what it is supposed to look like at the next timestamp, and compute some kind of loss, for example, L2 loss between the exact next frame and the worked version of the previous frame. This type of loss tries to address the issue of flickering without using some feature propagation techniques inside the network itself.
Okay, the next experiment that we perform is to try to address the temporal consistency problem just using features from correlation backbone and try to aggregate them using 3D convolutions. So another dimension of this convolution is not as spatial dimensions as 3D convolution is supposed to do, but the third dimension is just a time. So we process these frames at the same time, and in this fashion we use all this temporal information of all frames during the video. And this approach could be generalized a lot.
Yes, and as a more advanced baseline, we chose the deep remaster network, and we just make it smaller and call the small deep remaster network. And it is, and we can see it on this scheme. So the inputs are actually the frames of the video which are concatenated through the spatial dimension, which is temporal dimension, and also we have the reference images, which are actually colored and used to help our model to learn the color of the images through the attention block. But first we have the on this scheme we have the restoration network, which is colored orange. And this network actually we don't use because it is needed only to recover from the defected images, not defected images, but in our dataset we have only not defected images and images of high quality. Then we just put these inputs to the encoder block, and the output of encoder block goes to the attention block with reference images, encoded reference images. And then through the manipulations, we just use the decoder block and get colored outputs, which are actually predicted A and B spatials. Yes.
So after we performed some experiments, for the first experiments, we tried the colorization networks which rely on the FlowNet. So on the left, you can see the individual frames which are produced by the frame-wise colorization with additional flow loss on top of each colored frame. You can see that the colorization itself is not very good, even though we take the pre-trained colorization network, and the consistency between the frames in a single frame stack is not very good. So even after significant time of training, the results are not very impressive. The same goes for the model which relies on the flow net inside the network for warping features and propagating warped features forward and backward. Not only the colorization isn't good as it is, but this framework introduces some visual and significant artifacts. You can see the green pixels over there. And we observed that the longer the training, the more corrupted the image becomes. So unfortunately, the video colorization, which relies on FlowNet, doesn't work. So we decided to move on to some next models.
The next model that we used is just our backbone colorization for images with 3D convolution head, and surprisingly, it works the best with just one layer. For the head with some non-trivial initialization that was some kind of that we cannot achieve during the usual training, but the authors of the original paper of colorization for images suggested using a very specific ways for this one dimension layer, and fine-tuning this one layer with the whole colorization network gives us I would say impressive results.
We test our small deep master network on the unobserved SAM videos from another Davis dataset, and in the first row we can see that if the background of the video is fixed, but some elements are moving, our prediction of a small deep remaster network has a high quality, and on the other hand, in the second row, actually we can see that firstly the red square on the floor has a good quality, it is recognizable, but through the time it is vanishes because it is nature of inconsistency in the prediction. But and also we visit our neural networks on Andrei Rublev set on Andrei Rublev video at the fragment from the film, and the first was the small deep remaster net, and the second approach was the 2D convolutional head for CIC and fine-tuning. So we can see that actually, as we think that small deep remaster network it has overfitted on the references from Davis dataset, and actually can't use information from any of references, other references, to get the good colorization quality, and the image is flickering from time to time. But on the other hand, we can see that in the right image, in the right video, there is a more consistent video, and in the end of this video, we even can see that the quality is close to the good colorization.
So we analyzed a couple of methods for video colorization and end up with the result that the deep remaster network, which is based on attention mechanism and that uses consecutive frames with some convolutional backbone, works the best from all the methods that we checked. However, the problem of grayscale colorization of images is still ill-posed, and even existing methods of colorization of single images isn't very well solved. Thank you for your attention. If you have any questions, we will answer them later somehow.